All right, thank you very much. Yeah, you pronounce it quantinuum. So sorry for the grandiose title. The future of fault-tolerant quantum computation. It's not going to be that dramatic. That's my boss's idea. But I'm I'm very happy to talk about, as a scientist, all the experiments that we're doing to kind of first look into experimental fault-tolerant quantum computation on actual devices. Oh, wrong way. So we know, of course, that qubits are really noisy. The environment rapidly interacts with them. And it applies not just bit flip noise, like for classical computing, but as well as phase flips, potentially leakage, measurement errors, and so on. And also, due to just the nature of quantum mechanics, these states can be kind of difficult to protect. You have to do something more complicated than just what you do in classical error correction. And as we've heard from like John Preskill's talk yesterday and William Oliver's talk, as well as the talk before me and echoed throughout this conference, fault tolerance is probably something that will be necessary for doing quite complicated algorithms in the future for large-scale devices. And fault tolerance, kind of in a nutshell, means that you kind of accept the fact that qubits are fragile, and you compute in a way that kind of mitigates or kind of safeguards against that those faults harming the computation. So it tries to allow you to increase the coherence times of your computation, increases the number of operations that you can do to allow you to do more complicated algorithms. Nope. And it's kind of interesting to get a perspective on the past, how classical computing had to deal with errors, or the errors that they saw. So for vacuum tubes back in 1946 with the ENIAC, you had an error in 1 error per 10 to the 14 operations approximately. And for modern-ish transistors inside of a processor, you might experience an error in 10 to the 28 operations. So for the most part, you don't really need to deal with errors in classical computing. However, for more complicated things like servers and whatnot, you still have to consider errors. For example, with cosmic rays, as was mentioned before. And now quantum technologies are finally sort of starting to approach 1 error per 10 to the 3 operations or 1,000 operations. And this is also known as an error rate of 10 to the minus 3, or a fidelity of 99.9%. So 1 minus that error rate as a percentage is one measure of fidelity. So this once again highlights that quantum computing, at least at this current stage, is very error prone, and we need to deal with it. We really need to think about fault tolerance if we want to think about large-scale computing and complex algorithms. And backwards. For example, if we want to look at prime factorization, and beat RSA using Shor's algorithm, you might need, with some implementations, 10 to the 12 C-naughts, for example. So you'll probably need an error rate for the C-naught gate that's less than 10 to the minus 12. So that's significantly lower than what we're currently at. And one of the big tools in the toolbox of fault tolerance, one of the main ones, is quantum error correction. So quantum error correction, it uses the idea of redundancy just like in classical error correction, but you're encoding qubits, the information in qubits, into many other qubits. And this redundancy helps protect that information and suppress noise. And these encoded qubits are known as logical qubits. And this suppression of noise on the logical level allows you to hopefully do many more operations, enable much more complex algorithms in the future for large-scale devices. And so about a year ago at Q2B, I actually talked about our breakthrough with the STEAM code, or the distance 3 color code, using the Model H1 ion trap powered by Honeywell. At that time, it was utilizing 10 physical qubits, and it has a lot of nice, useful features in order to enable the protocol that we looked at. In particular, it has all-to-all connectivity, long coherence times, mid-circuit measurement reset, conditional gating, and classical processing of information. And sort of some of the highlights of those results, because I won't give the previous talk all over again, is that for the first time we were able to do repeated rounds of fault-tolerant quantum error correction. So that means that we were able, for this distance 3 code, to run these syndrome extraction rounds, these measurements that sort of detect and allow you to potentially correct errors, such that we can correct a single error event, either a bit flip, phase flip, or measurement error. And you want to make sure that you can repeat these things, because we kind of want to think about, we want to start moving towards large-scale quantum devices. We're not, of course, we're nowhere close to those right now, but we want to start trailblazing that and figuring out how these things actually work on real devices to keep us honest. I'm a theorist, but actually doing these things on real devices, you can't just throw away assumptions like you would in theory. And some of the nice features of the trap allowed us to do this feed forwarding and conditional application of gates, which allowed us to do conditional syndrome extraction. So just apply a syndrome extraction as needed, depending on previous rounds of syndrome extraction. So that's kind of a neat feature, but not necessarily a necessary thing. But yeah, particularly neat. But an important feature for the going towards large-scale fault-tolerant quantum computing is real-time determination of corrections. So that's determining during the computation the corrections that you need to do using this a classical algorithm called the decoding algorithm. And you want to do that because for arbitrary computations, for these long computations, you can't just look at the information after the fact, after you've ran the experiments. You need to determine the corrections during the computation, because there's certain operations that kind of don't allow you to push those corrections all the way to the end. So this is another first for full quantum error correction codes that can handle both phase and bit flip as well as measurement. And then, so that's where we currently, or were at a year ago. And I'll continue to talk about our advancements from that, but real fast. The experimental results from that talk was something like this, where what we see over here is the logical spam, which is basically the logical preparation of states, and then the destructive measurement of that state. And we get on average about 99.83% fidelity. And that's actually slightly higher than the physical spam rate, so that's kind of encouraging. At least for logical spam, we're able to get a little bit higher than, do a little bit better. But that's, of course, not the end of the story. You want to do more than just prepare and measure states. But these QEC cycles, these things that allow you to detect these errors and correct them, we got a fidelity of around 98% fidelity, so that's around an error rate of 2%. That's still not enough to have your logical computation be better than your physical computation, but it's still pretty decent fidelities. And we're trying to move towards the era in which logical computation becomes useful. Sorry. And from all this experiment, doing these things on actual devices, it was really useful because we were able to identify some key noise sources that are inhibiting us from having logical computation being better, like these QEC cycles having lower error rates than our leading physical error rates. In particular, leakage and dephasing were highlighted. So we now have located things to really hammer in on in the future. So it's, moving forward, that's an important thing to verify and to study. And so that was, I kind of went through that really fast, but if you're interested in those experiments, then please check out the archive. There's a lot of information about what we did. We tried to include all these flowcharts, pseudocode, and whatnot, and try to make the language fairly clear. So yeah, I definitely encourage you to check that out if you're interested. Now, moving on, we want to go beyond what we did a year ago. And for the STEAM code, for the distance 3 color code experiments, where we did real-time correction, so we did the determination of, we did the decoding after the end of each of these QEC cycles during the quantum computation, not after the fact. We utilize what's called a lookup table. And so it's basically, given the measurement results, we compile ahead of time what corrections should we do. And that becomes very costly as the number of syndromes goes up, as you increase the size of the code, and so on. So we can't keep on doing this in the future. So we need to push forward and push forward on even the classical side. And for example, in general, we want to do these algorithmic decoders. And one that's often studied is like minimum weight perfect matching. And basically what minimum weight perfect matching, a lot of the other algorithmic decoders are about is locating the changes in these measurement results and kind of seeing where they are in space-time and trying to find the most probable error that has caused those changes, those flips in the results. And so to enable us to do that, we've now implemented hybrid compute. So we actually have added a classical coprocessor to our quantum computing. So now we have both quantum computation running alongside and communicating with a classical coprocessor. And the information is moving back and forth. And we're able to write in generic things in classical languages like Rust, C, C++, etc. This then gets compiled to what's called WASM, or WebAssembly. And it basically defines a classical compute environment that we can call functions from and also store information within and manipulate information and process that classical information in that classical compute environment. And then this over here is just an example, a really small snippet of we use OpenChasm, extended version of that. And you might declare these classical registers as syndromes and the classical register for corrections, make some syndrome measurements to come up with these measurement results, do a function call to send that to the classical compute environment, and get out corrections. You also, because the classical compute environment is its own environment, you can also just store those corrections inside the classical compute environment and call the corrections back when you need them. Like whenever you encounter a logical non-Clifford gate, for example, and you actually have to apply or adapt the gate. So yeah, it's the quantum program and the classical program interact via basically function calls. And just as a sketch, I don't have fancy drawings because I'm just a scientist and I don't spend the time to do that, although I wish I did. This kind of is what it looks like in a very sketchy manner. You have this quantum developer that writes these in C or Rust or whatever, creates the WASM just by compiling to WASM, as also writes the quantum assembly language, sends that via our API to the device, and then you have the quantum machine working in tandem with the classical device, communicating information back and forth as necessary. So this enables us to do more generic decoding. Now, in this sort of checklist, in this things that we want to do and push forward in the future, I've made it orange or yellowish color. Because we have yet have a demonstration in which we're actually doing a general algorithmic device or decoder. However, we have utilized it. We've written decoders in Rust and ran using this hybrid compute environment for our next application that I'm going to be talking about. So we're still using these lookup tables, but because of what we did, the lookup table is kind of starting to explode already, and so we needed to utilize this classical compute environment. And so yeah, we want to scale up in the number of qubits. That will enable us to do larger codes, but also we want to look into logical, quantum error correction on 2 logical qubits. Now, actually, a couple of weeks ago, Protzler et al., an academic group out of Innsbruck and Aachen, actually has a really interesting result in which they did a fault-tolerant transversal logical control knot across 2 Steen codes or distance 3 color codes. So like what I was talking about before, the same sort of code. And we have also been working in that direction. So this is kind of the first announcement that we actually have done a logical 2-qubit gate. We now have 12 qubits in the trap. So that allows us to do 2 logical qubits using the 513 code, or the sometimes called as a perfect code. So it has 5 data qubits per logical qubit. And then we have 2 ancilla qubits that we can utilize to do fault-tolerant quantum error correction. Because of this particular code, we can't do these transversal gates that are really low depth and that are far easier to implement. Instead, what we did is we utilized the scheme by Yoder et al. That they came up with in around 2016 called PIECEABLE fault tolerance, or PIECEABLE fault tolerant gate. And so basically what happens is you have to break up the logical 2-qubit gate into 2 pieces in this case, where you do about 2/3 of it here, and then you have to do a QEC cycle in the middle to capture some of the, to prevent some bad errors to propagate through the circuit. And then you do the other 1/3 of the gate afterwards, and then you might do some QEC cycles following that. Now this QEC cycle in the middle, because it's measuring these operators across 2 logical qubits, it has a rather large depth, especially to do it fault tolerantly. So what we did is, and this is very high level, but we did a large QEC cycle across 2 logical qubits, and it in total requires about 100 CNOTs, so it's pretty deep. While the actual logical gate, the logical CNOT gate, is only comprised of 9 CNOTs. So to do this fault tolerantly, we utilize what's called flagging. So we use flag checks. I'm not going to go into that because I don't have enough time. But if you're interested, please see me and I'll be happy to explain it. So we use both flagging and unflagging. And then similarly to the previous results that we did a bunch of classical conditional gating depended on whether previous measurements are trivial or non-trivial. So we're sequentially using those 2 ancillas to measure in a flagged manner, a fault-tolerant manner, these different operators. And as soon as we get a non-trivial result, we then immediately conditionally branch over to these unflagged checks and remeasure all these checks using more naive circuits without this extra flagging. Otherwise, if all these measurements have been trivial, then we don't have to do this unflagged check. So this is another case where we can skip things that we don't need to do. So yeah, that is a really deep circuit that we had to do for this particular code. But it enabled us to do the logical gates, the logical CNOT gate fault tolerantly. So kind of to step back, what the logical CNOT or even a physical CNOT does is it takes the states, so over here, like in the Z basis, and it modifies it basically. So like 1, 0 goes to 1, 1. So this is the Z basis states, and then the X basis states, they have similar transition rules. And what these numbers over here represent is basically the probability, the average probability that these transitions happen, that you went from the initial input state to the final output state that you were expecting to go to, ideally. And so here, kind of listing basically the fidelities as we increase the fault tolerance, as we make the experiment more complicated. Here is just the logical spam, where we just initialize the logical states and then measure them out. So we had a fidelity of about 97%. That's pretty high. Still not as good as our physical span, though, for this particular code. With no QEC, if we just applied the logical gate without that QEC in the middle and end, those quantum error correction cycles, then we got a fidelity of around 97% again. So that's pretty decent. If we didn't include those flagging, but we still measured those unflagged checks, non-conditionally, we just measured them and then sent that in real time to the hybrid compute environment to come up with the corrections and then track those corrections, then we got a fidelity of around 80%. And then if we did the full shebang with 100 C0 gates to do that 2-qubit QEC cycle in between, then the fidelities drop to around 60%. So we expected this because it's really deep. There are codes like the color code that I mentioned before where the number of gates would be far smaller and we would get far better fidelities, at least we would expect so. But it's kind of interesting given the number of qubits that we have to start seeing that certain protocols have their advantages and disadvantages, and we can actually learn a bit again about the noise. So here is, once again, these transition rules at the bottom. This is the probability of being in a particular state after going from an initial state to a targeted or a final state. So this is the final state that we end up with, and the arrow points to the state that we want to be in after applying the logical C0 gate. And without applying corrections, so if we ignore the corrections during real time, we get this population. So what we see is that the X basis and the Z basis perform a little bit differently, and that's probably because we have some biased noise in the system, but we still need to study this because it's still hot off the press, so we still need some time to understand what's going on. And we see that the Z basis, the Z basis does a lot better. And also, interestingly, we see that the next highest probability on the Z basis is the state that's one bit flip. If you flip the bit of the second qubit, that's always the next highest probable state, which is interesting. And we have some ideas of why that might be occurring, but that's still sort of speculative. But it's kind of cool that we're starting to actually apply fault-tolerant quantum computation on actual devices and see what goes on and actually start to learn from them. And then if we apply the corrections, then the probabilities readjust themselves. It actually brings up the probability of the X basis significantly. They originally were around 30 to 40%, and it brings it up to about 60%-ish. And interestingly, it actually slightly reduces the probability of the Z basis, so going to the right state. So there's something weird going on there as well. This could potentially be improved if we had our decoder, if we made a decoder that was had more knowledge of our actual noise. We're just kind of using a generic decoder. So perhaps we can fix that or play around with it a bit and continue to improve these further, how we implement these protocols. So yeah, we're continuing to move forward. We enabled generic algorithmic decoding, although we don't have an example of that yet, but we're actually utilizing it. All the pieces are there, and we're moving towards that. And we did an actual logical 2-qubit gate, a control not gate, and for the first time in the world also applied quantum error correction to those two logical qubits, and did real-time decoding on those 2 logical qubits. And so in the future, of course, we want to continue to scale up. This will enable us to study more different codes and larger distance codes. One different code, for example, is that color code or the surface code, in which have transversal gates which would have much better fidelities for the logical 2-qubit gate. But hopefully from experimenting, just starting to experiment on fault-tolerant quantum error correction, doing it actually in the lab, we're going to learn a lot, and we're going to move, it'll be a great boon in moving towards the era in which we actually have logical quantum computation be better than physical quantum computation and start to expand the number of operations we can do. So yeah, thanks a lot for listening. Yeah.
Thank you. We have some time for questions.
Why didn't you do 2 7-qubit codes? It's just not enough ions?
Not enough ions, unfortunately. Yeah.
Just put in a few more ions.
That's what I tell the experimentalists. They don't listen.
Is anything of that nature in the plans?
Of course, I mean, we plan to scale up, yeah. So hopefully,
Next year.
Yeah, maybe next year, maybe.
Any other questions? Use the microphone.
Thank you. I was intrigued by your mention that you are working on using various classical resources to do error tracking and error decoding.
Mm-hmm.
So how do you upload and offload these tasks to, I think you're using a CPU type of hardware.
Yeah.
Can you do it, how fast can you do that?
I'm not a software developer, so I don't know all those speeds. I'm really a theorist. So unfortunately, but I can if you're interested in those things, I can point you to somewhere. There's some people in the conference I can have you talk to if you're interested in that. Yeah.
Any other questions? All right, well, let's thank our speaker again.